Good day, everyone. Thanks again to the chairman for the introduction. And ladies and gentlemen, our esteemed colleagues and distinguished guests, it is an honor to address you today on the topic of sustainability in polymer composites. So again, my name is Lim and I'm from Malaysia. I'm from University Malaysia Perlis. Okay, and I'm from Faculty of Chemical Engineering and Technology. So let me bring you to the content of the presentation today. Okay, it will actually cover the introduction and on polymer composite, natural fillers from waste, biocomposites, and also solution casting, and also the effect of solution casting on the properties of the composite. And then we will come to a conclusion on that. So basically, talking about polymer composite, I guess that most of us are very familiar with that. Okay, polymer composites are composites that made with the metric of polymer, may it be thermoplastic or thermoset. So their enhanced mechanical properties and lightweight nature, resistant to corrosion, their design flexibility, and also potential for sustainability make them a very valuable composite that has drawn a lot of attention, maybe from the industry and also from the academy as well. So they're used in multiple industry ranging from aerospace, automotive to construction, medical device. So it all shows that this polymer composite plays an important role. So as the technology evolves, the development and application of polymer composite will continue to expand, contributing to more sustainable, efficient, and also high-performance solution across various fields. And basically, we can find the application of polymer composite around us daily. And I believe most of us will encounter with polymer, okay, in our daily life. Okay, however, there's a concern of this, all right? The worldwide production of polymer has reached 400.3 million metric tons in the year of 2022. And this marked an increase of about 1.6% from the previous year. So this, if you can see from this figure or this graph, it shows that plastic production actually soared since 1950s. As we mentioned previously, plastic has been used in a variety of products, okay, and has displaced other materials such as wood, metals, and glass that were previously used for the application that plastic now dominate, right? So one of the main applications of plastic use is plastic packaging. And as we know, Asia is the largest plastic producer in the world right now, and China alone accounted for about 32% of global production in 2022. All right, and then since packaging tends to have a much lower product lifetime compared to other products such as construction or textile, so it is also dominant in terms of annual waste generation. So it is responsible for almost half of plastic global waste. Okay, as you can see from this data that I've actually obtained. Okay, from the internet itself, you can see that at the year of 2019, okay, the annual global plastic waste generation that you can see here, it's actually a lot of it has been generated. Okay, and basically, large portion of the polymer waste ended up in landfill. Okay, and the main problem is these polymer, they are non-biodegradable, which means that the microorganisms were not able to break them down even after they are ended up in landfill for many, many years. Okay, and these landfilling polymers can lead to long-term environmental problems. As the volume of the plastic waste continue to grow, landfills are becoming increasingly overburdened. And it is not only taken up valuable land space, but also create ongoing management issues. Okay, so this is the main focus and the main reason why the non-biodegradable polymer has caused a problems, okay, to the world nowadays. And that's why it triggers to us move shift our focus from the non-biodegradable polymer composite to a better alternative, which is known as a biocomposite. All right. So talking about this biocomposite, okay, basically it is taking from the natural fillers. Okay. So the shift towards this sustainable material, okay, is we would like to minimize the environmental impact, and we would like to create a more environmentally friendly products. These natural fillers derive from more renewable resources, offer an effective solution. Okay, so as we know that these natural fillers are derived from uh, biological resources such as plants, animals, and mineral. So from the slide, you can see that the plant fibers, which is hemp, flax, jute, canal, sisal, and also bamboo. They are very common plant fiber available. And also if it is the natural filler is taken from animal derived fillers such as wool, silk, chitosan, and then in terms of mineral fillers, it can take out from the top clay, calcium carbonate. Okay, so all of these they are very commonly available around us. And generally, these natural fillers, they have several advantages such as low density, they are very cost effective, and most importantly, they are biodegradable and they are derived from renewable source. And that's why it is able to help us to reduce our dependency on non-renewable petroleum-based product. And talking about these natural fillers from the waste, okay, we can also, in this study, I would like to focus on the waste from the plant, okay, especially from the agricultural waste, we known as agricultural residue. So it is a renewable resource, which is often abundantly available. As we're utilizing this waste, it reduces the environmental burden of disposal, and also it helps to promote a circular economy. As we can see here, these plant waste, they are always sourced locally, and therefore its usage in polymer composite can support local economies. In addition, these plant wastes are often low-cost material, which help to reduce the cost of the composite, right? And moreover, these plant-based fillers, they are generally biodegradable, okay, which help to reduce the long-term environmental impact of this composite material. So here, the example of the agricultural waste can be rice husk, sugarcane, bagasse, wheat straw, coconut husk, and palm kernel shell. So let me bring you to focus a little bit on this palm kernel shell. So as you can see from this picture, this is the oil palm, okay? And the picture in front, you will see this is the palm fruit, all right? So oil palm is very commonly available in Malaysia, okay? And originally, this oil palm is from Africa, okay? And then nowadays, it is cultivated in tropical America and Southeast Asia. So its fruit is actually radish fruit in large bunches, and it can weight ranges from 5 to about 50 kg. Okay, in each fruit, there is a single seed. Okay, as you can see here. Okay, so this is a single seed, and actually it's present in a huge bunches. Okay, and then within this seed itself, there is known as kernel. Okay, known as palm kernel. So which is surrounded by this soft part. Okay, and then the palm kernel shell is actually the hard, stony endocarps that surround the canal inside of it. Okay, so the pump canal that contains the canal oils are cracked down. Okay, they are cracked, and you will get canal and also the canal shell. So the canal will be sent for canal oil extraction, while the canal shell will be considered as a byproduct of the process, which is usually ended up in the landfill. And this byproduct of this oil pump actually cause a severe disposal issue, especially in Malaysia. So since Malaysia is one of the leading palm oil exporting countries, the massive production of this palm canal shell and also its disposal issue has leading to environmental concern. So that's why in our research, actually, we utilize this palm canal shell. We collect them, clean them, and then dry up and grind them into powder form. Okay, so if you can see in the picture here, the ground palm canal shell powder will be something like this in the picture, which is available in the powder form, and it is in the brown, brown color. Okay, it's in the brown. And then this is the SEM micrograph that shows you the palm canal shell powder. So it can be seen that the powder is actually in the form of irregular shape. It is in the particle form. Okay, so basically their size is in the range of micron. Because after we grind the powder, we actually will subject it to shaving process, and usually we'll take the lowest possible. I mean the smallest possible, which is about ranging about 75 micron and below. Okay, which is better for the incorporation of the filler into the polymer composite. All right, so here let me bring you to the findings of our several project, whereby we have actually incorporated palm canal shell in different types of thermoplastic, such as LDPE, low density polyethylene, polylactic acid, PLA, and also polymethyl methacrylic acid, PMMA. Okay, so you can see that the reinforcing effect of the filler actually depends very much on the interfacial bonding between the filler and the matrix itself. If you may see from the SEM figure in the right bottom here, you can see that the irregular shape of the palm canal shell, okay, once it is been added into the polymeric matrix, it actually does not bind closely with the matrix itself. But you will see that there is a gap exits between the palm canal shell filler and also the matrix. And this gap will become the stress concentrator, whereby it would compromise the mechanical properties of the composite very much. Okay, so in order for us to enhance the interfacial bonding between the filler and the matrix, generally we will try to add in a coupling agent or the chemical modification on the surfaces of this palm canal shell powder. Okay, you can see that actually we have tried to use different chemical treatments such as acrylic acid, AA. Okay, so in this one, we actually use LDPE with palm canal shell, and also we have treated it with acrylic acid. And you can see that even though the presence of the palm canal shell actually decreased the tensile properties of the LDPE, but with the addition of acrylic acid, it actually managed to improve the interfacial bonding between the filler and the matrix. Thus, it increased the tensile properties of the composite if you compare to the untreated counterparts. Okay, and similarly, you can see that the polylactic acid be added with palm canal shell. The presence of this butyl methacrylate acid also managed to improve the interfacial bonding between the filler and the matrix. And also, you can see that this one is a PMMA PKS. Okay, PMMA PKS composite, you can see that there is increase, okay, of the tensile strength with the addition of this stearic acid. So next, let me bring you to another project whereby we use a coupled husk as a filler. So what is this coupled husk, if you may ask, right? So coupled husk can be found in Malaysia easily. If you go to the park, okay, you can easily see this coupled tree, okay, present around the park. It is a very tall tree and it bears fruit known as couple fruit. Okay, as this couple fruit is red one, okay, the inside of it actually there is known as uh this the flesh, okay, the flesh of the couple fruit itself actually turn into like something like cottony feeling. Okay, so the locals actually use this couple fruit as a fill for pillows, quilts, and also soft toys. This is the usage of the local people in Malaysia here. We use this couple. And then this husk, whereby we collect the husk of this fruit and then we grind it into a powder form, okay? And we use it as a filler in this linear low density polyethylene composite. As you can see that the couple husk is actually hydrophilic, okay? So they are sensitive to moisture. That's why you can see that as we conduct the water absorption test, the water absorption is generally high, okay, as the filler loading is increased. However, when we utilize this lactic acid as a surface treatment on the couple husk, we actually manage to reduce the water absorption, okay, of this couple husk. And also we are able to enhance the physical bonding between the couple husk and the LLDPE metric. So you can see that it managed to enhance the tensile strength, okay, of this LLDPE PKS composite. So as well, you can notice that the thermal stability also has been improved when we applied this lactic acid as a chemical modification on the surface of couple husk. Okay, so basically you can see that we have tried to use several different agricultural residue waste into our thermoplastic. All right, so next, let me bring you to solution casting. Okay, so this solution casting is a very simple process. If you're talking about mechanical mixing that previously that I mentioned to you, how we incorporate the residue, okay, or the agricultural residue into thermoplastic to make it a composite. Generally, we are using the melt mixing. However, sometimes the melt mixing might not be efficient if we would like to produce a nanocomposite, okay? And also, the high temperature might not be so environmentally friendly, okay? In order for us to fabricate a composite. Hereby, we introduce solution casting. Okay, so this solution casting is basically a very simple and very economic approach. We does not require a complex design or large number of chemicals. Okay, and no additional energy requirement. So basically, we need to find a suitable solvent which can be used to dissolve the polymers and ensure the uniform dispersion of the fillers within the polymer matrix. And then this selection criteria for the polymer solvent will cover the solubility of the polymer within the solvent and also the boiling point of the solvent, the viscosity of the solvent, volatility of the solvent, and also its environmental impact. Okay, From here, you can see that the process of solution casting is a basically simple process whereby we just need to identify the suitable solvent for our polymer, and then we dissolve it, dissolve our polymer in the solvent. Okay, so usually this agitation will be needed in order for us to fasten up the dissolving process. And sometimes we also you enhance the dissolution of the polymer by adding a little bit heat, or meaning that you heat up a little bit on the solvent. And then finally, we will cast. Okay, we will cast the polymer solution onto a petri dish. Okay, so also sometimes we also use sonication. Okay, sonication in order to ensure the homogeneous dispersion of the fillers in the polymer solution. Okay, and then after casting, we will allow this cast film to be dried up. Okay, which means that the evaporation of the solvent will take place. So when we're talking about the evaporation of the solvent will take place, the selection of the solvent is crucial. Okay, so we don't want a harmful solution to be used for solution casting if we would like to focus on preserving our environment. So in our project, we actually utilize polymethyl methacrylic acid as a polymer. And for your information, toluene, dichloromethane, chloroform, and also acetone, they are the common solvent used to dissolve PMMA. So in our study, we have actually selected acetone as a solvent for PMMA, which is known as less toxic and less harmful, will possess less environmental impact, okay, to us. So that's why we select acetone as a solvent. Here we actually investigated the effect of solvent to metric ratio of this PMMA PKS composite. And as we know, previously we're talking about our metric and filler might not have a proper interfacial bonding. So likewise, we introduce stearic acid as coupling agent here in order to enhance, okay, the interfacial bonding between the filler and also the metric. So you can see that in this project, actually, we vary the solid to a solvent to metric, okay, ratio, okay. So you can see that as the longer solvent evaporation time was required for the formation, okay, of this PMMA PKS composite, with this increasing SM ratio, okay, you can see that it actually helps to improve or to enhance the tensile strength of the composite when we increase the ratio, meaning that more solvent has been added onto the fixed amount of this PMMA. All right, so the ratio actually will vary from 6:1, 7:1, 8:1, and also 9:1. So when there is a change of this ratio, it actually shows increasing of the tensile strength. So we believe that the longer solvent evaporation time will encourage the formation of these polymeric domains in a more organized way, which help to impede the crack growth, and also it will result in the improve of tensile strength. And if you look at this SEM figure, you can also see that the figure A, okay, actually denotes the, and also figure B, you shows that there is a presence of void, which indicate the detachment of these pound canal shell fillers during the tensile test. And also you can see that in this yellow arrow actually shows that there is a detached filler of the palm canal shell, okay, from this PMMA metric. Okay, so basically it shows that this is actually a result of this poor interfascial bonding. Okay, however, okay, the surface interfascial bonding actually can be improved when we utilize this stearic acid. Okay, this poor surface interfascial bonding actually will result poor load transfer from the matrix to the filler. Okay, and as a result, the mechanical properties actually has been compromised. Okay, if the matrix and the filler, they are combined without any chemical treatment, without any forms of coupling agent. So with that, we add in the stearic acid as a coupling agent, whereby you will see that in this blue circle, it shows that the palm canal shell actually has been bonded better, okay, with the PMMA metric. And you can see that the gap axis is actually very tiny, okay, meaning that the filler has been bonded very well with the metric. So with that, the loads can be transferred effectively, okay, from the metric to the filler. Thereby, it helps to enhance the mechanical properties of the sample, regardless the ratio of the SM. Okay. And then next, I also would like to share with you a little bit on the nano composite that we fabricate, okay, using PMMA and also silicon carbide. Okay, you can see that this one, the tensile strength of the treated PMMA silicon carbide composite was higher as compared to the untreated composite at similar loading. Okay, it shows that the treated silicon carbide, okay, can be used to prevent agglomeration, okay, of these silicon carbide particles in the PMMA composite. And in this context, actually, we use silane, okay, to treat the silicon carbide nanoparticles. And you can see that the proper bonding between the SiC filler and the polymer matrix is crucial, okay, for this load transfer mechanism. And from here, you can see that the SEM micrograph of tensile fracture surface for virgin PMMA thin film, okay, as compared to this PMMA SiC composite. Okay, so figure A is actually a virgin PMMA thin film, whereby you can see that it's actually form a brittle properties, as you can see, a smooth fracture surface. Okay, so they are rigid, they are amorphous nature, and that's why there is no flexibility that you can see. Okay, that's why they are very prone to cracking and fracture when they are subjected under this tensile stress. However, when we try to incorporate silicon carbide into this composite, you can notice that particle clustering and also agglomeration actually take place between within this PMMA metric. And these agglomerates can create uneven distribution and protrusion on the surface of the composite, and thereby increase the roughness of the composite surface. So in B and C, you can notice that the rough surface, okay, and this is due to the amount of the silicon carbide that has been incorporated into the PMMA composite. So as the filler loading continue to increase from 0.5 to 1.0, so there is higher probability for these filler particles clustering and also agglomeration, okay? And this will continue to increase the roughness. And you can also notice that there are filler detachment take place, okay, in these two SEM micrograph. However, when we try to treat the silicon carbide with silane, and you will notice that the surface start to become smoother. Okay, and the filler detachment notice what actually has been reduced. Lesser filler detachment can be observed. Okay, in figure D. And also, as we increase the filler loading to 1.0, smooth surface also be observed. All right, and as we enlarge the SEM at a higher magnification, okay, at 4,000, you can notice that filler detachment actually do take place, but the possibility actually reduce compared to those untreated SiC composite. All right, so I think that's all for my sharing. And the use, I would like to bring us to our conclusion today. The use of plant waste as a natural filler in polymer composite, okay? And also the use of solution casting by using non-toxic solvent is very crucial if we would like to move or we like to step towards achieving this sustainability in material science. Okay, by leveraging renewable resources, enhancing their mechanical properties, okay, we would like to utilize as much as possible sustainable materials rather than focus on the non-renewable petroleum-based polymer alone. Okay, so our ultimate purpose would be in a innovative solution to create high performance, eco-friendly composite that will benefit the industry and also the environment as well. So as we move forward, it will be our collective responsibility to continue in our research, in innovating, and also in advocating sustainable solution. So we can work together to achieve a greener and more sustainable future. All right, I think that's all from me, and thank you very much for your attention.